Okay, let me walk through the solutions for assessment review 6 so that you can see me work them out and not just have to look at them on the page static. All right, so in the first problem, you're asked to fit a quadratic polynomial to these 3 points in order to estimate the sine curve. So you have a set of x values and y values here. We know that the sine of 0 is 0, the sine of pi over 2 is 1, and the sine of pi is 0. So what you can do in MATLAB is you can let x be 0, pi over 2, pi. Let y be 0, 1, 0. Use the polyfit function for x, y, and 2, and the result is going to give you the coefficients for a quadratic that you are in the form that you're accustomed to. So the quadratic you're going to get as a result should be negative 0.4053 x squared plus 1.2732 x, and the third coefficient comes up as 0, so there is no constant term here, which is interesting. If you take y and let x equal pi over 3 and throw that through a calculator or MATLAB, you should get 0.8888, which is actually really close to the actual value for the sine of pi over 3. You can check that, but so there you go. That's problem number 1.
So it keeps my head and my neck aligned. So now
Okay, so let's look at problem number 2. Let's let W be the set of all A, which are m by n matrices, such that A squared is equal to A. Now, this is not going to be a vector subspace, so all we need to do is to provide a single counterexample. The easiest way to do this is to let B be the identity matrix. You should note that the identity squared is equal to I, so this would imply that B is in W. Okay, so let's consider B plus B. Okay, so B plus B is the same as I plus I, which is equal to 2I, right? So this means that B plus B squared is 2I squared, which is 4I squared, which is 4I. Now, note, 4I does not equal 2I, right? So this means that if I add B to itself, I don't get something that's in W. So this means that we are not closed under addition. If we're not closed under addition, W is not a vector subspace. All right, so that's the answer to number 2. Okay, so problem number 3 is a network problem, right? So we're going to start by articulating the current going through the nodes. So I1 plus I3 has to equal I2. That's how node 1 works. I2 plus, or sorry, has to equal I1 plus I4. That's from node 2. I5 has to equal I3 plus I6, that's node 3. I4 plus I6 has to equal I5. That's node 4. So let's look at path 1. Path 1 has 2 resistors. So 2 times I1 plus 4 times I2 has to be 10 volts. In path 2, you have 4 resistors. So 4 times I1 plus, sorry, that's I2, plus I3 plus 2 times I4 plus 2 times I5 should equal 17 volts. And then in path 3, 2 times I5 plus 4 times I6 should equal 14 volts. All right, so you can balance each of those equations. You're going to get the following matrix: 1, negative 1, 1, 0, 0, 0, 0, negative 1, 1, 0, negative 1, 0, 0, 0, 0, 0, negative 1, 0, 1, negative 1, 0, 0, 0, 0, 1, negative 1, 1, 0, 2, 4, and then 4 zeros gets me the 10 volts. 0, 4, 1, 2, 2, 0 gets me the 17 volts. And 0, 0, 0, 0, 2, 4 gets me that last 14 volts in path 3. If you Gauss-Jordan this, it comes out nice and neat. Just kind of filling in the rest of the matrix here. Okay, so this gives me my list of currents. So I1 has 1 amp, I2 has 2 amps, I3 has 1 amp, I4 has 1 amp, I5 has 3 amps, and I6 has 2 amps. And that is the solution to this network problem. So there you have it. That's number 3. All right, so at this point in the course, we should recognize that if I make columns or rows out of the 3 vectors in 4, and the result gives me the identity matrix, then what I'm getting is something that is spanning. Okay, so, and that will happen if and only if I'm spanning, because here's what's going on. This is the correct size. Because if it's going to span R3, it has to have a dimension of 3, so it has 3 vectors. So, if I get the identity matrix, that means that I am linearly independent and right size, which implies spanning. If I don't get the identity matrix, that means that I am not linearly independent, but I am the right size, which means that I also have to be not spanning, because if I was, it's either a basis or it's not, right? So let's kind of live with that a little bit. So I can literally put these vectors into columns in this. If I take Gauss-Jordan here, I end up with 1, 0, -1, 0, 1, 0, 0, 0, 0. So this means that I don't have a basis, but I do have the right dimension. So I am not spanning, right? Because right dimension and spanning would make this a basis, and this is clearly not a basis. So it has to be not spanning. All right, so there you go. That is an answer for number 4. It just suffices to show that the Gauss-Jordan of the matrix doesn't give me the identity. Okay. All right. Number 5. To get to the steady state matrix, you have to go kind of high on this. What I ended up doing was taking like p to the 100th power times the current state. That gave me 200, 300, 500. If I took p to the 101st power times the current state, I also got 200, 300, 500. So at least at that point, I understand that if I put the X matrix 200, 300, 500 into the P matrix, I'm going to get back 200, 300, 500, which means my steady state matrix is 200, 300, 500, and that solves problem number 5. All right, problem number 6 asks us first, is this a basis? And then if it is, to write the matrix as a linear combination of the vectors in S. So build the column matrix, 1, 4, 7, 3, 0, 1, 2, 1, 2. If I apply Gauss-Jordan to that, I get back the identity, which tells me that I have a basis. Okay, so to get the coefficients for the linear combination, all I have to do is augment this matrix, 2, 1, 2, with the end result, which is 8, 3, 8. I take Gauss-Jordan. I'm going to get on the left-hand side here, I'm going to get the identity. And the augment is going to come up as 1, 3, -1. So this tells me that 1 times 1, 4, 7 plus 3 times 3, 0, 1 minus 2, 1, 2, the last coefficient is -1, should give me 8, 3, 8, and you can check that. It works out quite nicely. All right, so let's look on number 7. Number 7 gives me this matrix. You literally can enter that matrix into MATLAB and ask for the rank of A. The rank of A here is 2. If you then know that this is an n by n matrix, so this is 4 by 4, 4 minus the rank of A should give me the nullity, which is also 2, and that's it. That's the whole problem. Okay, so number 8 is asking me for the general solution to a system of equations using a homogeneous part and a particular solution. So the first thing we need to do is work out the homogeneous solution. So we enter this in with a 0. We perform Gauss-Jordan on that, and we end up with 1, -2, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0. So this means that x minus 2y is 0, and z is 0. If you let y be t, this means x is 2t, y is t, and z is 0, so this can be written as, this is my homogeneous vector, and this can be written as t times 2, 1, 0. Okay, so now I take Gauss-Jordan again, and I apply the 8, the 28, negative 28, and 12. And this is going to give me 1, negative 2, 0, 4, 0, 0, 1, 4, or sorry, 0, 0, 0, 0, 0, which means that my particular solution is 4, 0, 0. So the general solution will be t times 210 plus 400, and for any value of t, that vector will solve this system of equations. All right, so that's all 8 problems in the review. I hope this is helpful. Thank you.